Okay, we're back. Second video. Okay, I didn't want to do it all in one big video.
You're crazy!
I am crazy. I know. I wanted to make two. I don't know. Most people don't watch whole videos, so that way they're smaller. Okay, so now we're going to do a t-test for slope. So very similar to a t-interval. We're going to run a t-test for slope. So I'm gonna help you out with the example because I don't know. I could write out all the stuff, hypothesis, conditions. We already know the conditions. Same conditions that we had in the other video for the interval. Hypothesis, right? I'm going to show you in the problem how to write the hypotheses because it's not going to change very often. And then the mechanics, I'll show you as we do it. It's mostly in the printout here, so there's not a whole lot you do. And then the conclusion, I'll help you with that. So, do the data give convincing evidence at the alpha of 0.01 of a positive linear relationship between state test score and percent attendance? Okay, so this data was taken for some Algebra 1 students in Texas, and they found that the more you attended school, the more you got correct answers on some probably math tests, state math tests. So they wanted to show that there's a relationship between attending school and your score on this math test. Now there's variation, we understand, but it looks like a nice positive pattern. Now, what does a t-test for slope look like? Okay, so t-test for slope is sort of like a confidence interval. We're trying to figure out what is the true slope of the population, not of our sample, the population. So the null hypothesis will always be that the true slope of the population, which is the symbol we use, capital beta, equals 0. The null hypothesis is always that there basically is no slope, that it's a horizontal relationship, which means there's no relationship at all. That's what we're trying to disprove, right? We don't want that. We assume that's true. We're trying to prove that's not true. So on this problem, they asked you to prove that it's positive. So we're trying to prove that the true slope is greater than 0. Okay, so that is typically your hypothesis every time. This is usually always going to be equal to 0, and your alternative will be greater than, or it could be less than, or it could be just not equal, depending on what they ask you in the problem. So this one, they're asking you to prove it's a positive relationship. So since they said to me, prove it's a positive relationship, I'm going to prove it's greater than 0. There's your hypothesis. Done. Make sure you use the beta symbol, capital B with the tail on the bottom here. Conditions. Same conditions that we did in the intervals. Do we have a random sample? Well, I hope we have a random sample of these Algebra 1 students. We don't have that many, right? There's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's only 11. 11 is way less than 10% of all algebra students in Texas, I guess. And then the next one, right, looks like a line pattern. Scatter plot looks linear. Happy about that. And then they didn't give you a residual plot, so I can't comment on that. And I don't know what all the residuals are, so I can't see a histogram of them. So I assume residuals are normally distributed. It'd be nice if they would have given me the residuals, because then we could have at least looked at them. But that's our assumption there on the condition. Okay, so conditions are done. So now we go to the mechanics. Okay. Well, the mechanics, you guys, is we need to get the test statistic and we need to get a p-value. So there's lots of ways to get it, okay? Lots of ways to get it. So to get your test statistic, that is going to be your t-score. Your t-score on this problem is going to be what is the slope that you got on your regression line minus the null hypothesis, which was 0 for the null answer, divided by the standard error of your slope. That is it. That's all you're doing, okay? So you're saying, wait a sec, Mr. Sheldon, this is all given to me in the printout. Yes, it is all given to you in the printout, okay?
I like it a lot.
So you just look and there is your slope because attendance was the x variable. So that means the coefficient of the x variable is my slope. And your standard error of the slope is right there. So if I were doing this by hand, which I end up won't, but if I were, it would be 0.57 minus 0 divided by 0.062. That's it. That's all you're doing. Let's see what we get. I don't even know. 0.57 minus 0. Why am I minusing 0? Divided by 0.062. I'm getting like 9.19. So I'm getting a test statistic of 9.19. That wasn't tough, right? That was actually one of your easier ones we've ever done. So 9.19 for that one. And then your p-value, right, you could look that up in the table. Remember, your degrees of freedom are going to be n minus 2. So this one, your degrees of freedom are going to be 9. And you could go ahead and you could look that up on your table. So that's one way. Watch. We go to our table, 9 degrees of freedom. Okay. What was our t-score? 9.19? That's off the chart. That's less than 0.0005. So we're going to have a really low p-value. Where's another place to get the p-value? Well, calculator, right? You could go, remember I showed you that one time I said you're probably never going to use it. You could go to TCDF and you could say, okay, I want my boundary to be 9.19 to infinity, 1 e to the 99th. Degrees of freedom are 9. And let's see what the p-value is. Oh my gosh, tiny. 3.5, 3.6 basically times 10 to the negative 6. So tiny, okay? Tiny, tiny, tiny. Now, I want to show you that this is actually located. Check this out. Oh my gosh, I feel like it's cheating, but look. What? 9.18? 9.19? Rounding. That's the only issue. They obviously rounded the standard error, so it's actually, this is more right. So this is, they let the computer do it for you. That's the test statistic. That, I know they didn't write it, that is the p-value. So there should have been a number there, but it was so small they wrote 0 because it's like 0.00005 zeros and then 36. So right, it's super small. So they didn't write it there. But it should have been there if it wasn't as small. So this is crazy.
You're crazy.
They give you the answers. There's your test. You don't have to do anything by hand if you don't want to. You could be like, boom, test score 9.18, p-value 0, conclusion time. So this is why, like, there's almost no work on these for mechanics if they give you all the printout. Now, could they be mean and not give you everything? Yes. They could block the T and the P. I've seen them on exams block T and P, only give you these two to force you to go do it by hand, which means I'm then forced to also use TCDF on my calculator. So I'm going to put a little note here. I use TCDF with my t-score as my lower boundary, infinity is my upper boundary, and I put in my degrees of freedom. So that's how you can do it if you're forced to do it, but you don't have to do it that way because most of the time they're going to give you everything on here. Awesome. So see, before we didn't need to, you guys never needed to look at anything past here. Remember, this was your linear regression line, remember? So the formula for this one would have been that the tests, what was it, number of correct answers or something was the y? Number of correct answers is your y. So it would have been correct answers was your y variable. Predicted, remember, correct answers, equals 0.57 times the attendance percentage plus, or no, minus 7.69. That would have been your linear regression line from that printout. That's all we learned way back in chapter, I don't even remember, chapter 8. That was what we learned way back in chapter 8, how to read the printout and pull off the slope and the y-intercept. How do I know which one's which? The x variable will be listed. The one next to that is the slope, and the other one is the y-intercept. So that's it. So like if they give you these printouts, don't look at these two. Don't you dare go look at these two. These are the y-intercept stuff. We don't even mess with those. So don't even look at the t and the p for the y-intercept. Even the standard error, we don't even look at those. Okay? So you're going to focus on all of these ones. Those are the ones we want to look at because that's going to be your standard error if you had to do a t-interval. That's going to be your t-score for your test statistic, and that's going to be your p-value from that test statistic. It's amazing, right? Amazing.
I swear I've seen a lot of stuff in my life, but that was awesome.
It was. The printouts are awesome. Now your conclusion, you guys, this is like all the other conclusions you've ever done. Who cares that it's slope? So we have a really small p-value. So I reject the null because 3.6 times 10 to the negative 6 is so small, right? Or less than, or less, I should have put, they gave us an alpha on this one. Less than alpha was 0.01, way less than that. So I have evidence that the slope is positive because that was our alternative hypothesis. We were trying to prove the slope was positive, and we did it. We have pretty good proof that it's positive slope. So as you come to school more, we think your number of correct answers goes up on this math test. There you go. So there you go. That's not too bad, right? That was we just did that in 13 minutes. 13 minutes, you just ran a test. T-test for slope. And most of it's given to you, so there's not much to do, right? Now you can test for slope. The nice thing is you know when these come up. You have a graph, a scatter plot with a line on it. Right? You know it's different than all the other ones. So I have one more problem. What I would recommend you do is just pause it, try and do it, and then start the video and watch me do it. Okay? So pause it right now, try and do it, and then start the video and watch me do it. Okay, here we go. Okay, you've attempted the problem by now. Now it's time to go over it. So two AP Stats students wondered if there was a linear relationship between the speed you drive and how much drink you spill when driving on bumpy, dirty roads. To find out, they filled a cup of water, placed it in the cup holder, drove down a bumpy road at different speeds, and recorded how much water spilled out. They did 25 trials 5 trials at each speed. So you see they did 5 trials at each speed. A scatter plot of the data is shown there with the analysis done for you over here. Do the data provide convincing evidence at the alpha of 0.05 that a linear relationship actually exists? Assume conditions have been met. Yes, conditions are met. Okay, here we go. Here we go.
Light bulb.
Okay, so we're going to do it. Hypotheses. There is no slope. That is a null hypothesis. The slope is non-existent, right? Horizontal line. We're trying to prove, well, what do they ask? Do the data provide convincing evidence of a linear relationship? They didn't say positive or negative. They just said it had to be a linear relationship. So this is going to be not equal to 0. Two-tailed test, not equal to 0, because they didn't say positive or negative. Might have gotten you there. Might have tricked you. Okay, so there's that. Conditions met. Yes, we move on. I love it when those are met. Okay, next one. Run the mechanics. Well, the printout, they were being mean to you. They covered up the t-scores that would have been here and the p-values that would have been here. So they covered them up because they want to see if you can do it by hand. But I'm good. I can do it by hand. I should write the name of it. I'm doing a t-test for slope. And my test statistic will be my slope that I got. There's my x variable. So my slope is the 1.52 minus 0 divided by the standard error. The standard error is right here for the slope, 0.179. So when you do that on your calculator, 1.52 minus 0 divided by 0.179, holy moly, this gives us a t-score of 8.49. That is humongous. So let's see how many degrees of freedom I have before we do this. So our degrees of freedom were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I only count 12 on there. Oh, there's 3 of those. Okay, so there's 25. So it's going to be 25 minus 2. It's going to be 23. Okay, you can't see the dots because there's 3 dots right there, 2 dots right there. Okay, so 23 is your degrees of freedom. So I'm going to get my calculator because they didn't give me the printout. And I'm going to put in my limit, 8.49, your test statistic. And we're going to go to infinity on that. And we're going to put in 23 degrees of freedom. And it's going to give us the tail. The tail is 7.62 times 10 to the negative 9. So the p-value is 7.62 times 10 to the negative 9. That is the p-value way up here. I can barely fit it, right? It's 8.49 right there. That's this part right here. Well, this, we just did a two-tailed test, not a one-tailed test. So because this was a two-tailed test, I need to double what the calculator gave me. So take that, times it by 2, and that is your p, which isn't much better, 1.52 times 10 to the negative 8th. But now at least I have the right p-value. So there's the correct p-value. There's your correct test statistic. And you have 23 degrees of freedom, right? Probably all the 3 things that they're going to look for on your mechanics: test statistic, degrees of freedom, p-value, done. So your conclusion should have been, you definitely are going to reject the null because my p-value is less than alpha. I think it was 0.05 on this one. And then that means, did they tell us 0.05? Yeah. That means that we have evidence that there is a linear relationship, context, I haven't put any context in yet, between driving speed and how much water spills. Right? We have evidence that it's a positive slope. Okay, we actually have evidence it's positive slope. But that is it. So hopefully that helps. You've now run 2 tests on t-test for slopes. Very straightforward. And we did 1 t-interval. So hopefully that helps. I should try to unlock some problems for you to practice. I'll look and see on AP Classroom if there's some problems and I'll put them on. Thanks for watching, guys. Hopefully it didn't bore you and you're still awake out there.